All right, guys, next step. Remember, I started out this little discussion of simple chemical kinetics by saying, I've got this reaction that goes A to B, and it's just totally unimolecular. I don't have to worry about it. It just goes one way, it's irreversible, right? That happens. There are lots of situations where that's true. There are lots and lots of situations, maybe most situations, where that's not true, where we have to think about what happens going back in the other direction, right? Okay, and the way you would write this down thinking about rates, right, is you would say, well, I've got a forward rate constant. Um, and the typical way to do this is to give it a subscript, because sometimes you have multiple of these. So this would be, say, a 1. And one of the common notations, there are multiple, people do this in different ways. The one I like is to say, okay, I've got one step, k sub 1. The reverse step is going to be k sub minus 1, right? That minus means going back the other direction. Okay. Wow. Now what do we do? Well, let's think about it sort of the way we started out, right? Which was we're thinking about how much A we've got per unit time. All right, so remember again, the way we started out before, we got the rate at which the concentration of A decreases with respect to time. That's how we started. So we're comfortable there. And we can say, well, we know if we keep the minus sign over on that side, right? Because we're thinking about the rate at which A changes. We know that that's going to be proportional to the amount of A we've got, concentration of A we've got, times that forward unimolecular rate constant, right? That's more or less the rate equation we came up with to begin with, right? That describes the loss of A. But now we got another one. Shoot. We're not only losing A, we're making it. Wow. That means we got an input. If this equation, right, or this part of the equation, the way I've drawn it, if that describes the output, the loss, the pipe going out, if you want to think back to my water tank analogy, problem now is we got a pipe coming in, right? We're also making it, which means our overall expression now has got to be equal to minus K minus 1 concentration of B. It's minus, right? Because the first part, that K1 times A, that's the rate at which A is disappearing. We got to subtract from that the rate at which we're making A, right? Which would be that unimolecular K sub minus 1 times concentration of B we've got. Okay, so that's our next new rate equation. What do we do? Well, next time, the next lecture, I'll show you something more. I'll show you the true solution, the complete solution, general solution to that. Today, let's make it a little bit easier. Let's make a simple assumption. What if we go back to this idea that we're at equilibrium? We take this process, but at equilibrium, what has to be true? At equilibrium, there can be no net change in the concentration of A, right? If we're at equilibrium, there's no change with the concentration of A with respect to time, which means we can write something down like this. It means minus D concentration of A with respect to time has to just be equal to 0, which means the rate equation we just wrote down also has to be equal to 0. Oh, okay, well, that's not so bad. If we can assume equilibrium, that's pretty easy, because now I can go, all right, fine. That means K1 times concentration of A has to just be equal to K minus 1 concentration of B, right? Oh, that's cool, right? What that says is at equilibrium, the rate of the forward and the reverse reactions must be completely balanced. There can't be any change, right? Because that's an assumption of equilibrium. Well, what that also means is that I can rearrange this expression this way. I can say, well, that means that the ratio of the forward and the reverse rate constants has to just be equal to concentration of B divided by the concentration of A, right? at equilibrium. We know what that expression is equal to, right? That's the equilibrium constant. And so what this means, or whether way we could write this down, is that the equilibrium constant for a simple unimolecular process like this is simply equal to the ratio of the forward and the reverse rate constants. Turns out that's going to be true for even more complicated cases, though the form of that overall rate constant in the forward and reverse direction gets more complex. But this basic idea that the equilibrium constant is going to be equal to the forward and reverse rate constants holds across the board, right? So that's a really important one to remember. Okay.